In our infinite Riemann sum homework, we want to be able to rewrite integrals as infinite Riemann sums and infinite Riemann sums as integrals. Before we get into these problems, let's make sure we have a good understanding of what we're trying to do here. If we take an integral from a to b of f of x, what that means is between x equals a and x equals b, what is that area between x equals a, x equals b, the x-axis, and f of x? We started making Riemann sums, and we can estimate with a right Riemann sum or a left Riemann sum. It doesn't really matter for what we're going to be doing in a second, because what you'll see is that to get a really good estimate of the area, instead of having a few rectangles, we want more rectangles. The more rectangles we have, the better our estimate ends up being, and we get closer to the actual integral. And eventually, if we take a limit and the number of rectangles goes up to infinity, we'll cover the area exactly. Now let's look at how we add up all those rectangles. We're going to be talking about the number n, which is going to be the number of rectangles. So we're going to see how many rectangles we have, and there are going to be a few things that keep coming up. How do we find the area of this rectangle? Well, it's length times width. And the width of the rectangle is always going to be the same thing. The width of the rectangle is going to be how much distance there is here divided by the number of rectangles, right? If the distance here is b minus a, it's the distance between b and a. So the width is always going to be b minus a divided by how many rectangles there are. If there are 4 rectangles, you're going to take this length and split it up into 4 parts. That will be the width. The length is a lot harder. The length depends on what the function is, how high you are at different places, and it's going to change depending on what rectangle you're at. So what we're going to do is we have this idea that we're going to take the limit as the number of rectangles goes to infinity, and we're going to add up n rectangles one at a time. This means we're going to add rectangle 1 plus rectangle 2 plus rectangle 3 plus rectangle 4 until we get to rectangle number n. The lengths will always be delta x, how wide the rectangles are, and that will always be b minus a over n. The widths are going to, if we start from the left side, it'll start at whatever a is, f of a. So what we'll see in just a second is that there's a pretty easy way to see it. We're going to get f of a, that's the first rectangle, right, will be f of a, plus how far over have you gone? The first rectangle, maybe is right there, but the second rectangle is going to be at a different height, and that height is going to be f of this x value plus however many distances you've gone. And what that is going to be is the width of each rectangle times what rectangle are you on. If you're on the first rectangle, you only need to move over once to get to this x value, a plus b minus a over n. If we go over to the next rectangle, it'll be a plus b minus a over n, which is the width of a rectangle, times 2. And so we end up with this. Let's see how this actually works when we want to do this. I think I want to start with this one, c. We want to take this integral and we want to rewrite it as an infinite sum. Well, it's going to be the limit as the number of rectangles goes to infinity. That part will always be the same. We're going to be summing from k equals 1 to infinity, and now we have to find the width. We can start at the end by saying, hey, what's the distance between -2 and 0? That distance is 2 over n. This is the width of each rectangle because the integral has a length of, the x values go from -2 to 2. And if we split it up into n rectangles, that's the width. Now we're going to have to do f of. So what's going to happen is for x is going to get, the length is going to be 3 times, our x is -2 because that's where the integral starts, plus our width of a rectangle times k. Oh man, I should have left myself more room here. I apologize. I'm going to have to scratch this out. This is squared because that's what it's 3x squared. And the x is going to be this guy, plus 2 times the exact same x, and then times the width. Some things to notice. The width will show up here, here, everywhere there's an x, as well as the times the width at the end. This is length times width. This is the y value at each different rectangle. Let's do one more, and let's do this one going the other direction. Here we clearly have the width. So the integral is going to have to go, it's going to have a length of 2. The difference between b and a is going to have to be 2. So maybe it goes from 3 to 5, or from 7 to 9, or from 0 to 2. And here's our f of x. It's going to be 2 times, clearly this is x squared. And the reason I can tell this is x is because we've got this 2k over n and this 4 plus. This 4 plus is the bottom of the integral. That's the lowest y value. So if you haven't added any rectangle lengths, you'll be doing 2 times 4 squared. Again, because I know that the width is 2, this is 6. Notice that 2 over n showed up both here and here. This is written slightly differently than we did it before, but that's okay. Okay, let's go to the back and see how we can match these. If I take an integral and I want to match it up with a sum, the first thing I want to see is what is the width? This width is 2. So it's going to be only ones that are 2 over n. So no, 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 maybe. No, no, maybe. No, maybe, no. So there's only 3 possible ones here. It might be. This is the easier version. You want to be able to do this without matching, but if you can't, that's okay. Let's see what we've got. So now our f of x is going to have to be 2 times something squared. And it starts at 4, so it's going to be 4 plus 2 over n times k, or 2k over n. Now let's see if we can match one up that looks like that of our possibilities. No, there's this random plus 10 that doesn't seem to match. Here it is. It's right here. Now, this is written differently. You'll notice that up here I had 4 plus 2 over n times k. Here it's 4 plus 2k over n. Well, that's fine. It's the same thing. It's just written slightly differently. So that's how we can match up going that direction. The other direction, let's say we want to find this one. 4 over n, that has to be the difference in the integral. The integral has to have a length of 4. And so this is a length of 2, 0 to 2. This is a length of 2, 6 minus 4. Length of 2, maybe it's this one, 0 to 4. Maybe it's this one, 1 to 5. That's a length of 4. Maybe it's this one, 0 to 4. That's a length of 4. So it's going to be one of these 3. Pretty quickly we can tell it's 2 times, here's that 4 over n. That's the width, times k squared. So here's our 2x squared plus 3. And very quickly we can tell it matches up to this one. I hope that helps. You do really want to be able to do the advanced version. Sometimes on the AP exam, they'll give you an integral, and you'll need to, it's usually a multiple choice, you'll need to match it up with a Riemann sum. Sometimes they will give you a Riemann sum, and you have to match it up with the correct integral. One more thing to note, I've been saying k equals 1 the whole time. That's for a right Riemann sum. That's because we already start off 1 away from where the function begins. We're starting 1 rectangle away. If we wanted to make it be a left Riemann sum, we would use k equals 0. One more thing. Ooh, this is a great example for it. You'll notice that this is already simplified. Sometimes you want to simplify, like this is 4 over n times k squared. That's clearly what's going on here, but that's only 16 k squared over n squared. And so clearly it was getting multiplied by 2. It might just look like it's x squared plus 3, but it's actually 2x squared plus 3 because part of the x was 4 over n getting squared, and so there has to be a 2 there. Sometimes you might have to simplify. So when you get something like this, we could always square this binomial. If I wanted to simplify this, like the AP exam could put that this is, we know how to square a binomial. We square the first one, multiply these two together and double it. So that's going to be 16k over n plus square the last one, 4k squared over n squared. And we could multiply this out. They could have very easily rewritten it like this. And you would have to recognize that. It would still have the 2 over n here. But anyway, I hope this is helpful.